Today we're going to be talking about mesh analysis. And much like nodal analysis, mesh analysis can be thought of as an algorithm. In nodal analysis, we learned that we were just going to apply multiple iterations of Kirchhoff's current law in order to solve for every unknown voltage in a circuit. In mesh analysis, we are going to apply multiple iterations of Kirchhoff's voltage law in order to determine every unknown current in a circuit. Okay? So much like we did in our last lecture, we are going to learn this process by applying it to circuits. So I'm going to start with the following circuit where I have a 21-volt source, a 5-ohm resistor like so, a 10-ohm resistor. Let's make this guy an 8-ohm resistor, 20-ohm resistor through which a current IX flows, a 7-ohm resistor, and then let's make this a dependent voltage source, positive polarity on the bottom, and let's call this 3IX. Like so. So this is the circuit that we are going to be analyzing and learning to apply the mesh analysis technique to. Okay. So our first step is to identify our meshes. So I have one mesh here, one mesh here, and one mesh here, right? Recall from our very first class meeting where we defined a mesh to be any loop that doesn't contain any smaller loops. So all three of these window panes here effectively constitute a mesh. Our next step will be to assign mesh currents. So a mesh current is a current that flows around the mesh. So for this leftmost mesh, let's call this I1. For this middle mesh, let's call this mesh current IB. And for this right-hand mesh, let's call this mesh current IC. We are now going to express our controlling variable in terms of our mesh currents. So what's our controlling variable in this circuit? The current IX, absolutely. So the current flowing down through that 20-ohm resistor. Okay. So in the case of a current like this, what we're effectively looking for is the mesh current that's flowing in the same direction as indicated by IX as it passes through that 20-ohm resistor, minus the mesh current that's flowing in the opposite direction as it passes through that 20-ohm resistor. So which of our three mesh currents is in the same direction as IX as it goes around their clockwise path? IB, okay? So IB is going to get a positive sign. Which of the mesh currents is in the opposite direction of IX as it flows around its clockwise path? IC. So we're just going to have IB minus IC. Anybody have any questions? about that? IB, as it goes around the clockwise path, right? So I did this in green, right? So when it's flowing down this branch, it's flowing in the exact same direction as IX. Whereas when IC goes around its clockwise path, it's flowing in the opposite direction of the current IX. So it's whatever mesh current is in the same direction minus whatever mesh current is in the opposite direction. We have not assumed a polarity for any terminals as of yet. We will do that momentarily when we start writing our Kirchhoff's voltage law equations, which will be our next step. So step number 4 will be to, that's not a W, write KVL equations for each mesh. So let's start around mesh 1. Starting from the bottom left-hand corner, what are we going to have? Okay. So we're going to see the negative polarity terminal of our 21 volt source first. So we're going to have negative 21 volts. Then we're going to have the voltage drop across this 5 ohm resistor. Now this one's going to be particularly easy because there's only one current flowing through the 5 ohm resistor. It's that current I1. So we're just going to call this term plus 5 ohms times I1. All right. Now we have the 10 ohm resistor. So when we are applying Kirchhoff's voltage law around mesh 1, we are making an assumption here. And the assumption is that the current I1 is going to be flowing into the positive polarity terminal of any resistor it sees. So when we get to the 10 ohm resistor, I1 is flowing into the positive polarity terminal. I don't know why I did 1, B, and C, by the way, that's confusing as hell. Let's make that A. Yeah, sorry. Yep. Sorry about that. I don't know what the heck I was thinking. So this is going to look like IA minus IB, right? So when we follow IA around, effectively all of the IA terms should have positive signs, and anything flowing in the opposite direction of IA is going to wind up getting a negative sign. And we have completed our path around this mesh, so we set this all equal to 0. So let's move along now to KVL at mesh B. So now we're following IB around its clockwise path. So anything that gets has IB will have a positive sign, and any current we see opposite to IB will get a negative sign. So from that, what should my first term in my KVL expression look like? Alex. Yeah. How do I express the voltage drop across this 10 ohm resistor with positive polarity on bottom in terms of my mesh currents? Paying attention might be a good thing. Troy, how do I do it? Yep. Times 10 ohms. Yep. So 10 ohms, IB minus IA. The next thing we're going to see is the 8 ohm resistor. So what should my term look like for that particular resistor, Hojun? 8 ohms times IB, absolutely correct. And lastly, we come to our 20 ohm resistor. Parker, what should my term for the 20 ohm resistor look like? I disagree for a couple of different reasons. So first, we're following IB around, so it should have the positive sign. IC is in the opposite direction, so it should be IB minus IC. And if we're using Ohm's law, it should be current times resistance, not current divided by resistance. So take another crack at it. Times 20 ohms, absolutely right. Set this equal to 0. Lastly, we're going to have our KVL equation around mesh C. Carrie, what's my first term in this KVL equation going to be? So starting from the bottom left-hand corner, which is how I like to write my Kirchhoff's voltage law equations, the first thing I see is the 20 ohm resistor. So I know it's going to be 20 ohms times something. I'm following mesh current IC around its clockwise path. So IC should have the positive sign. And there is a mesh current flowing opposite the direction of IC. So put all that together and tell me what it should be. Exactly right. 20 ohms times IC minus IB. Alia, what should my next term be? Seven ohms times IC. And what should my last term be? Danielle. So is it plus or minus? Minus, because we see the negative polarity terminal of the voltage source first. Absolutely. So minus 3ix is equal to 0. So we currently have 4 equations and 4 unknowns. We can break this down into a 3 equation, 3 unknown system by making the substitution that Danielle suggested and simply replace that Ix with IB minus IC. So at this point, we are able to solve this system of equations. So let's do just that. So I'm using a calculator that can only solve a 3x3 system. So my first equation is going to be my KVL at mesh A equation. My coefficient for variable IA is going to be 5 plus 10. My coefficient for variable IB is going to be negative 10. My coefficient for variable IC is 0. And my constant term is going to be 21, positive 21, when I move that over to the right-hand side of the equal sign. For my KVL at mesh B equation, my coefficient for IA is negative 10. My coefficient for IB is 10 plus 8 plus 20. My coefficient for IC is negative 20. My constant term is 0. Now for my KVL at mesh C equation, my coefficient for IA is going to be 0. My coefficient for IB is going to be negative 20 minus 3. The minus 3 comes from the substitution of Ix is equal to IB minus IC into that last term. My coefficient for IC is going to be 20 plus 7 minus negative 3, so plus 3. And my constant term is 0. Solving this system of equations, I get IA is equal to 119 over 60 amps, so just shy of 2 amps. IB is 7/8 of an amp. and IC is 161 over 240. So did anybody else get those numbers, or did I type stuff into my calculator poorly? I got a couple of people raising their hands, so let's assume that the math was correct. Okay. So now that we know these mesh currents, how can we use them to find other quantities? For example, if I wanted to find the power absorbed by the 8 ohm resistor, what would that be in terms of my mesh currents? 8 times IB squared, absolutely right. What if I wanted the power supplied by my 21 volt source? (21 volts times IA, because the mesh current IA is flowing into the negative polarity terminal. And if we want supplied power, we're looking for the current flowing into the negative polarity terminal. So 21 volts times IA. What about the power absorbed by my dependent source? So 3IX times IC would be the power supplied by that source. I want the power absorbed, right? Because IC is flowing into the negative polarity terminal. So it would be negative 3IX, which we know to be IB minus IC times IC, right? So once we know those three mesh currents, we can find out literally anything else that we could possibly want about the circuit just using Ohm's law or our simple power relationships. Yes. Fantastic question. So Isaiah just asked, when assigning mesh currents, should we always do them counterclockwise or clockwise? So I assign all of mine as clockwise pretty much all of the time. I say pretty much all of the time because when I'm dealing with circuits that contain magnetically coupled inductors, I might choose to make my mesh currents go in opposite directions of each other just to give me more positive signs. But we're not going to have to worry about that in this class at all. So practically speaking, it literally does not matter which direction you choose for your mesh currents, or even if they're all the same direction, or if you just mismatch them. So for example, if IB were flowing in the opposite direction, how would that change things? Well, effectively everywhere in these equations where we see IB, we would replace it with negative IB because it would be in the opposite direction, right? So that would look like a negative IB here, a positive there, negative here, et cetera, et cetera, et cetera. I choose erase all of these to use a clockwise direction because I typically write my KVL equations starting from the bottom left-hand corner and going clockwise around the circuit. I know some of you mechanical engineers are inclined to write things in the opposite direction because of your second moment of inertia. Yeah, which if that floats your boat, go for it. Okay, well, you be weird. All right. So, any questions about this mesh analysis procedure here? So hopefully some of you may have noticed that the circuit that we analyzed only contained voltage sources, right? So now we need to figure out what falls apart when current sources are included. Okay, so Christina just asked if you would use a technique like this with superposition. You absolutely can. That being said, I would argue that if using superposition, you're going to wind up setting up a system of equations anyway, you should have probably just used nodular mesh and skipped having to set up multiple systems of equations. Yeah. There's nothing wrong with it by any stretch of the imagination, but it just seems like more work. Yeah. Yeah, like I said, if excuse me, if you're going to try to use superposition and you realize that you're going to wind up having to set up a system of equations, then just work it from the beginning using nodular mesh and just set up one system of equations to solve the whole thing instead of multiple systems of equations to get the same result. Okay, so let's see. Stop. There we go. All right. This will be a good one. All right, so we're going to look at a circuit now that contains current sources, and we're going to see how to take care of those. Put this out. I want to make this a dependent. Let's call this voltage Vx. Ground this bottom thing here. Okay, so our first few steps should remain exactly the same. So we need to identify our meshes. So this will be one mesh. This will be a mesh. This will be a mesh. And this will be a mesh. Now I'm going to label my mesh currents. So IA, B, C, and D. I'm going to express my controlling variables in terms of my mesh currents. So in this case, my controlling variable is the voltage Vx, the drop across the 6 ohm resistor, positive polarity on top, negative polarity on bottom. Cade, help me out here, please. 15. So it's the voltage drop across a 6 ohm resistor, right? So 6 ohms is going to be involved in there somewhere, okay? So we're using Ohm's law. So we're really looking for the total amount of current that's flowing into the positive polarity terminal. So we're going to have to include IC as well. So effectively, anytime a resistor is shared between two meshes, we are going to have two mesh currents flowing through it, okay? From the direction that we've chosen to draw our mesh currents, so clockwise around each of these loops, IA is flowing into the positive polarity terminal, so it's going to get a positive sign. IC is flowing into the negative polarity terminal, so it's going to get a negative sign. So we're going to have 6 ohms times IA minus IC. All right, so something new that we are going to have to do here, because we have current sources, is we are going to have to write a current relationship equation for each current source. So let's start with the 2 amp source. How do I relate that 2 amps of current that's being driven by that source to my mesh currents? Logan, you have any thoughts? IA, absolutely right. So as IA flows around its clockwise path, it's literally in the exact same direction as our current source, so it's just IA. Okay. Now, let's look at the 4 amp source, right? So the 4 amp source is between two meshes. So it's going to have a contribution from mesh current IB and mesh current IC. Walker, what do you think that relationship should be? So which current is flowing in the same direction as the 4 amp source as it goes around its clockwise path? Okay, which current is going in the opposite direction? So what's the relationship? Absolutely right. Lastly, we have the 2Vx dependent source. So how am I going to express that in terms of my mesh currents, John? Negative ID. Absolutely correct. I had 3 current sources. I now have 3 current relationship equations. Okay, so step 5 is going to be something new as well, and we're going to see how things break here. So I won't give it a name just yet. So what would happen if I tried to write a KVL equation around mesh A? What would my first term be? So 6 ohms times IA minus IC is a voltage plus 2 amps. So can I add voltage and current together? Absolutely not. Okay. So what Hojun is struggling with is an inability to express the voltage drop across the current source in terms of mesh currents. And he's struggling with that because it literally can't be done. Okay. So anytime we have a current current source on the perimeter of the circuit, so on the outside edge, we are only going to have the current relationship equation, right? So all of the information we need for mesh current A is this guy right here. Okay. So because that 2 amp current source is on the outside edge, we cannot write a KVL equation. Same thing for the 2Vx dependent current source on the right-hand side. We literally cannot write a KVL equation. Now, let's look at what's going on with the 4 amp source, right? So it's not on the edge, so we could try to come up with something, but we're gonna wind up having the exact same problem. So what I mean by that is, let me do these in pink. So if we were trying to write a KVL equation around mesh B, the voltage drop across the 15 ohm resistor is easy enough to do. The voltage drop across the 8 ohm resistor is easy enough to do. But the voltage drop across this current source cannot be done, okay? We could call it VCS from right to left or something like that. And as we tried to write a KVL equation around mesh C, we would have the voltage drop across the 6 ohm resistor with this polarity, the voltage drop across this current source with this polarity, the voltage drop across the 8 ohm resistor with this polarity, and then the voltage drop across the 10 ohm resistor with this polarity. So we have that exact same voltage that we can't express in terms of our mesh currents of the opposite polarities. So what we would do is we would simply add those two equations together. That is the exact same thing as applying the super mesh technique, okay? So let's talk about a super mesh really quickly. When the current source is on the outside, so on the outside, we can't write an equation for the voltage drop across any current source. When the current source is on the perimeter, there's no alternative path that we can take either. When a current source is on the interior of the circuit, there is an alternative path that we can take, and we're about to define what that is. And we call that path a super mesh. Okay. So a super mesh is the smallest possible combination of meshes that avoids taking the voltage drop over the current source, okay? So since our mesh current, or excuse me, since the 4 amp current is shared between meshes B and C, then our super mesh should contain just meshes B and C. So instead of going around this one and then around this one, we are instead going to take this path for our Kirchhoff's voltage law equation because it avoids taking the voltage drop across that 4 amp source, okay? So we should see a super mesh for almost all interior current sources. And the reason why I say almost all is because we'll have some rare special occasions where effectively a super mesh touches a mesh that has, well, we'll see one in the in-class assignment. I'll work it for you guys in a moment to better explain what's going on, okay? So our step number 5 here is going to be to write a KVL equation for all super meshes that contain only interior current sources. So sorry, I scrolled way too far. Starting from the bottom left-hand corner, what should my first term be? Brody. Shit, not Brody. Carson. Damn it. Sorry for looking you straight in the face and then calling you your brother's name. Times what? Times 6 ohms. Absolutely right. Again, I apologize for that. So 6 ohms times IC minus IA. All right. What should my next term be? Emily. Exactly right. IB times 15 ohms. So we're avoiding that current source. Mason, what would my next term look like? So that 10 ohm resistor is shared between meshes C and D. So why isn't mesh current D making a contribution? There we go. So 10 ohms times IC minus ID. Set this equal to 0. And then step 6, which we're not actually even going to need, would be to write a KVL equation for all remaining meshes that do not contain a perimeter current source. And for this circuit, none of those meshes exist. Right? So we should have a total of 5 equations, right? We have our 4 mesh currents and then our controlling variable Vx. So 1, 2, 3, 4, 5 equations. And then we could solve this if we wanted to. I'm not going to because I want to move along to bigger and better things. At this point, it's just using your calculator correctly or MathCAD correctly, right? All right, so I want to look at in-class assignment problem number 3. So in this particular problem, you are asked to use mesh analysis to determine the voltage Vx and the power supplied by each of the sources in the circuit shown below, okay? So our first step would be to define our mesh currents. I'm actually going to combine steps 1 and 2 into a single step, so I'm going to identify and label them all in one go. So here's our mesh current, let's call it IA. Here's our mesh current, IB. Here's our mesh current, IC. That's steps 1 and 2 taken care of. Okay. I have a controlling variable, so I need to write my controlling variable relationship. So that's going to be Vx is equal to something. All right, so first things here, I have intentionally put the terminals across the voltage Vx in a confusing as way as possible because I like to be a jerk to you guys on occasion. Okay. So how could we write that voltage Vx in terms of our mesh currents? Well, there are really two ways that we could do it, right? So we could say that Vx would be the voltage drop across, let's use this gray color. The 16 ohm resistor, positive polarity on bottom, plus the voltage drop across the 5 ohm resistor, like so. That's one way that we could do it. An easier way would be to recognize that it's literally just the voltage drop across the 21 ohm resistor. Okay. Either of those paths will work, but the voltage drop across the 21 ohm resistor is easier, and I'm lazy, so that's how I'm going to do it. Okay. So what should the voltage drop across the 21 ohm resistor look like with positive polarity on the right, negative polarity on the left? Isaiah, you want to take a crack at it? So IA minus IC times 21 ohms. I agree with that. Okay. All right, now we need our current relationship equations. So let's start with the 7 amp source because that one's a little bit easier. So how do I express my 7 amp current source in terms of my mesh currents? Just IC. All right. Now let's do the dependent current source. So 0.5 Vx. How do I express that current in terms of my mesh currents? Patrick. So that dependent source is shared between two meshes. So it should have two mesh currents. There we go. IC minus IB. Great job. So we have an interior current source. So we should expect to have to write a KVL equation around a supermesh. Okay. So our interior current source is shared between meshes B and C. So the path that we would be expected to take would look something like this. Why can't we write a KVL equation around this path? Because this path contains a current source, right? And we can't write a KVL equation for a path that contains a current source. So in this case, our supermesh contains a perimeter current source, so we can't write a KVL equation. Okay, so this is the exception that we talked about earlier. Anytime you have a situation like this, you're just going to have current relationships that govern things. So because there is an interior current source that we're trying to avoid taking the voltage drop over. So we presently have 3 equations and we have 4 unknowns, our 3 mesh currents as well as the voltage Vx. So where's our last equation going to come from? Mesh A, absolutely right. Going down to step 6, we need to write our KVL equations for any remaining meshes that do not contain a perimeter current source, and that is mesh A. So we would have 5 ohms times IA plus 16 ohms times IA minus IB plus 21 ohms times IA minus IC, set it equal to 0. And we now have a four equation, four unknown system that we can solve doing a simple substitution. Because everywhere we see IC, we can just treat that as 7 amps. Or everywhere we see Vx, we could treat that as 21 IA minus IC. So realistically, we could actually get this down to a 2 equation, 2 unknown system if we wanted to make enough substitutions, but I'm lazy and I don't. Okay. All right, so I'll let you guys finish up the remainder of this problem on your own. I just wanted to show you an example of where that super mesh thing can also fall apart. All right, so does anybody have any questions? Hojun? Add it. We're applying Kirchhoff's voltage law, and a voltage source just gives us a known voltage, so we literally just add it. Fantastic question. So Hojun just asked when you would use nodal analysis versus when you would use mesh analysis. So to me, whichever is going to give me the smaller system of equations is the one that I would choose, okay? So when I look at a problem, I first look at, can I solve this just using Ohm's law, KCL, KVL, or voltage division or current division? I look for the easy methods first. Only if I can't use those do I go towards nodal or mesh. And then I make that decision based entirely off of which is going to give me the smaller system of equations. If they're going to give me the same size system of equations, then I base my answer off of whether or not I'm trying to solve for a voltage or a current. If I'm trying to solve for a voltage, I would use nodal analysis. If I'm trying to solve for a current, I would use mesh analysis. So that's my process.